In this video, we're going to take a look at electron configurations that are anomalies. In other words, that are exceptions to what we would expect when making the electron configuration. So the anomalies or the exceptions to the electron configuration rules are generally found in group 6 and group 11 of the periodic table. So when you see group 6 and group 11 elements, that's where you'll find those exceptions. So these group 6 and these group 11 elements over here within the transition metals. So we have those main exceptions there. We'll take a look at what the main exceptions are, and we'll understand why those exceptions are the way they are. But again, group 6 and group 11, so we're going to see things like CR, CU, MO, AG, W, and AU. So these are the main exceptions we'll be discussing. And there's also some ions that are exceptions as well. So if you try to make the electron configuration for, suppose, chromium, you would get this based on the rules that we learned in class. You'd fill out your orbital diagrams, and you get something that looks like this in the last few that you need to fill out. So 1, 2, 3, 4. So this would be the S, and this would be the last D that you fill out in the chromium energy diagram. And if you do the same thing for copper, you would get, well, this over here, using the electron configuration rules that we came up with. And so it would look something like this in the little diagrams. You'd have the 4s2, and then you'd have your 3d9. So you'd have your 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that's what you'd predict based on the rules that we learned in class. However, the actual experimental electron configuration is as follows. For chromium, rather than being 4s2, 3d4, we have argon 4s1, 3d5. So that's for chromium. Notice that it's still the same number of electrons. However, they're placed in different areas. You'll notice that rather than have 2 in the S over here, we have 1, and then rather than have 4 in the D, we have 5. So it's as if we took the 1 that we had in the S over here and put it into here instead. So in other words, it looks more like this. We have the 4s1 here, and then the 3d5. So this is something you need to know, that this is an exception. If you write this, this is predicted, but it's incorrect. This is the one that's correct here. And for copper, if you were to do this same exercise, you try to write it out, you would get this as your predicted, but it's actually wrong. The actual configuration, the experimental configuration, is actually AR 4s1. Interesting, it looks like we took out 1 from the S and we put it in the D over here. So it looks more like this. And then the D is full. I'm not following Hund's rule here because it's full, so I'm just pairing right away because I know it'll be full anyways. But in reality, you'd have to follow Hund's rule, place singly, then pair after. Just don't tell anyone. So why is this the case? Why is it that the chromium and the copper have these unexpected electron configurations based on the way we were told to follow the rules to build the configurations? Well, the reason has to do with stability as usual. Generally, when we look at the order of stability of subshells and orbitals, what we find is that the empty or full are more stable than half-filled orbitals, and those are more stable than partially filled. So in other words, not half. So if you could get all full, that's the most stable. If you can't get all full, half filled is next, and then partially filled would be after that. So if you can't get all full everywhere, maybe your goal is to get some combination of full and half filled. That's a possibility. So you'll notice that over here we have in this predicted one we have a full, but then this is partially filled over here, and so that's not very stable. This is not stable because it's partially filled. This full one here is stable, but that partially filled one is not. So we could actually make this whole configuration more stable by taking one of the electrons here and then putting it into the D subshell to make it half full. So if we do that, now here's what we get. We get a half full over here, half full here, and half full here. So this configuration is more stable than the predicted one because you have two half-filled sublevels, whereas in the previous one you have a full one, yes, but then you have this partially filled one here that's not half-filled, and that makes it unstable. So by making half and half, that's more stable there. And it's a similar reason for the copper configuration. So notice that, this is full, so yes, that's stable, great. But this one over here is not stable because it's partially filled. It's not even half. It's not half filled. It's partially filled. So what could we do? Well, if you take this electron here and put it into this d orbital over here, now you get a full and a half full. There's no more partially filled. So this is way more stable than the previous configuration. So we now have a full, a half full, and a full, which is more stable than our partially filled that we had over here. And that explains why this is the actual electron configuration of chromium and copper. And the same reasoning applies to the other ones in group 6 and group 11. So you can try out the following examples. So we'll do MO, the atom, and then we'll do the iron ions as well. So I would pause the video, try it yourself first for both of them, and then afterwards check the work. So here, let's go find how many electrons MO has. MO has if we go to our periodic table, 42 electrons to place. So we have 42 electrons we need to place for MO. And I'm going to place them into this diagram here. So 1, 2, 3, 4. Let's fill these out. So far that's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. And then 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, and 42. And so if you look at this carefully, you would think that the electron configuration, based on what you drew here, is going to be, so predicted, this is what we predict here, predicted 1s2, 2s2, 2p2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then 4d4. And so that's your predicted. And of course, if you want to do the noble gas shorthand notation, you could do Kr 5s2 3d4. Now, this element is in group 6, so it's one of those that's going to be an exception. So again, take a look over here. We are in group 6. Let's go to our periodic table right here. So we're going to have an exception, and it's pretty easy to spot this exception if you look carefully in the final areas where we placed our electrons. Here we have a full, and here we have a partially filled. So what we can do is we can grab one of these electrons from the 5s and put it into the 4d over here. And that will be a more stable arrangement. So what we're going to do is we're going to redraw this in the more stable arrangement. So I'm going to erase this. And I'm going to redraw it in its most stable arrangement just to show you that here. So this was, whoops, I just put it back where it was. So the electron that was in 5s2, one of them was grabbed and put into the 4d. This one remains there. And so what you notice is that this is a more stable arrangement because this is now half full, and this is also half full. Whereas before we had a partially filled, which was not very stable. So that's what we're doing here is we're taking one electron from here and putting it into here. So same process here. And so the actual configuration is this instead: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d5. Or you could say krypton, 5s1 half full, 3d. Whoops, did I make a mistake there earlier? I think I did. That was a 4D that I should have done. And so you were probably screaming the whole time saying, no, that's a mistake, it's a mistake. So 4D4 and 4D4 over here. (4D5). So half and half full, more stable overall. And that there's an example of another exception to the electron configuration where your predicted would be different from what your actual is due to stability of the full and half filled shell over the partially filled shells. So you can try the iron ions yourself. A little hint I'll give here is when you're trying the iron ions, first try to build them without thinking about stability too much, and then rearrange for better stability. So start with the neutral, then create the ion, and if you see there's a better way to get a better stability from that, then you can go ahead and try that out. We'll take that up in the next video, and we'll finish up with the orbital diagrams as well in the next video.